I don't want information about the midterm recorded. I don't know. Not really. I don't care, but it's not really course material. Okay, so you've seen assignment 6. How many of you have done tutorials? Yeah. And how did that go? Yep.
For me, it was literally a struggle getting PyGame working because it wasn't cooperating with my older operating system, so I couldn't get it working. I just got working right now.
Okay, so there are some issues, installation issues. One is 32-bit versus 64-bit. So the PyGame distribution that you get from the official PyGame site is a 32-bit distribution. If you've already installed 64-bit Python, that's a problem. It's not going to work for you. There is somebody who's posted a link to a 64-bit installation, but that doesn't always work. And you know, if you're really struggling with that, perhaps the best thing to do is just uninstall Python, the 64-bit version, uninstall everything, go and delete the Python 27 directory, because the uninstaller doesn't always take everything out of there. That can cause problems later on. And then reinstall the 32-bit versions of both Python and PyGame. That seems to be a solution that works. So just blast everything away and start over. Doesn't take that long. And you know, if you've been working in your Python 27 directory, make sure you copy your work out of there. But you shouldn't really be working there anyway. How about for those who had working machines? So I know that the tutorial room was screwed up. They installed PyGame on something like 5 machines inside the room. That supposedly was fixed yesterday, so it should be available on all the machines. So if you had a working system, how far did you get? Yeah.
I found it was a lot easier than some of the other languages that I tried to use graphics in. So I really didn't. I found the tutorial was really helpful.
Okay. Good. Yeah.
Sorry, just going back to PyGame, is there a way to check whether or not you're going 32 or 64 bit?
I think if you just run Python interactive, I'm not sure. I'm not sure under Windows what this. So you get this little message here that tells about the system. I don't know if that will tell you that under Windows. It might tell you that it's 32 or 64-bit. I'm not sure. Yeah, it does? Okay. So just fire up Python in the interactive mode and see what that tells you. But the 64-bit version of PyGame is apparently a little dodgy. So maybe the 32-bit version is the easiest. Yeah.
Is there a way to run in the 32-bit version? Why not run in the 64-bit version?
So what do you mean?
Well, because to run Python with PyGame working, I had to run Python 2.7 that 32-bit version.
Yeah. Well, if you don't have a 64-bit version installed and you just installed Python 2.7 or 2-7, then that should be the default Python. Then either you have to specify it or wipe out the 64-bit version and reinstall. I mean, you can also look in your shell, for example, the shells support things like aliases, so you can redefine Python to mean Python dash whatever. Yeah. Okay. So did anybody get the whole tutorial exercise done? You got something animated, moving back and forth, and yeah. Okay. So a few of you. Did anybody fail to get even anything drawn on the screen? Okay. Good. So you got somewhere. And these seem like dumb little exercises, and they are, because we have to start somewhere, but they're basically us building up our toolkit so that when we're ready to make a real game, we have the skills to do so. We know how to do all of the basic things. So today I want to look at start making a game or something like a game. It'll start out maybe as just as a simulation because it won't have any interaction, and eventually we'll turn it into a game. And so here's my vision of this this game, and here it is. Well, this isn't all of it. Some stuff has been commented out. The main character in the game is an ant. Here it is. A little insect, or I guess it's an arachnid. And this ant is a hungry ant, so it wants to eat food. So different pieces of food will appear on the screen here, and the ant by itself will go off and eat that food. Now, what's going to happen is, and maybe it's easier to draw this. So we'll have our screen, we'll have our little ant, and some food will appear here. And the ant, without any intervention from us, is going to decide on which piece of food that it wants, move towards it, and then eat it. And once it's eaten it, some other food will appear somewhere else to replace that, and then the ant will decide again where it wants to go. It'll move towards it and eat it. So that's not a very exciting game. It's just watching this thing walking around and eating food. It won't even be a great animation. You won't really see it eating it. The food will just disappear when it gets there. So what's the catch? Well, the catch is that there will be sometimes poison. And that poison sometimes will get in the way of the ant. And if the ant walks over the poison, it gets, it swallows it, eats it, gets the poison stuck on its body, whatever, and dies. And so the interactive part of the game will be, I'm not sure yet how it's going to work, but removing the poison somehow. Maybe clicking on it, maybe it's not so immediate, but maybe you put a bomb on the poison, it takes a few seconds for the bomb to go off. I don't know. I haven't fully decided that, but that's the idea. And it's a good place to start because the first thing we can focus on is getting the whole ant food thing working. So then it's just a simulation, maybe even the poison, and then we can worry about exactly how the user will go about rescuing this ant or saving it from being poisoned. So there's the current version of this thing. And here's the code for it. It's the usual stuff, except there's some extra functions defined here that end up being useful. They show up, in almost every game that you write, and so I've just decided to abstract those off as functions. So one thing is if I have 2 points, P and Q, so points have these 2 coordinates, so P at 0 and P at 1, Q at 0 and Q at 1. What's the distance between 2 points? Well, you guys have seen somewhere how to compute the distance between 2 points before? That's something they still teach in high school, right? Yeah, okay. So you take the difference in the x coordinates and square that, and then you add the difference in the y coordinates and square that. So this is the difference in the x coordinates. This is the difference in the x coordinates squared. This is the difference in the y coordinates squared. And then you have to take the square root of that whole thing. So that gives you the distance between the 2 points, P and Q, where each point is a pair of coordinates. Okay. Loading images is something that we do frequently, and I want to keep things a little bit tidy here. So if I look in this directory, there's one file, game.py. There's a backup being kept by my editor. That's not so important. But the images go in a separate subdirectory. And so do the sounds. There's none there right now. And so we have a helper method called loadImage. You just give it the file name. It takes care of appending the directory to that and loading that thing. And finally, something that we frequently do is, by default, when we draw things in PyGame and in most places, you basically specify what you're drawing, so it's always drawing one rectangle into another rectangle, and you specify the top left corner of the rectangle that you're drawing, the position of it. And that's kind of annoying because it tends to lead to everything being lopsided. So we just wrote a little helper function that takes one rectangle called surface1 and draws it onto surface2 so that the center of surface1 is at this position. Okay? So that's easy to do. You get the rectangle that's associated with surface1, and you move it to that position minus the width of the rectangle over 2, and that y-coordinate of that position minus the height of that rectangle over 2. So now the center of surface 1 will go at that position rather than the top left corner. And then surface 2, we blit it onto surface 2. Okay, so this is a game that screams out for objects. So there should be ants, there should be food, there should be poison. And if you think about it, even for a very brief time, all these objects are quite similar. They have some stuff that's in common. Well, for one thing, they are all on-screen objects. They all appear on screen. There may be some other objects that are not so obvious, maybe the state of the game or something that's a little bit less obvious, but ants, poison, and fruit, or food, they all appear on the screen. So we have this superclass which is GameObject. And our game objects have a couple of things. They have a position. That's where they're drawn. And they have an image, which in PyGame terminology is called a surface. So remember, in PyGame, surfaces are just these rectangles, and they're really images. So there's a surface every time you load an image. There's a surface anytime you make a piece of text. You get a surface, a rectangle that holds that thing. And the screen itself is a surface that you draw stuff onto. Okay, so we have this game object. It's going to have a position and an image. And what are the things this game object can do? Well, so it can initialize itself. You specify the position and you specify the image. So it takes a copy of the image. And the position, we're a little bit careful about how we do this. We make a copy of the position and we make sure that it's a list. So this says copy the input thing. So if the input is an array, we'll copy it. If the input is a tuple, we'll copy it. And we want a list. And that's because, well, this should be, if the people are using this correctly, this will be some object that has two parts. Maybe it's a tuple with two parts, or maybe it's a list with two parts, an x-coordinate and a y-coordinate. But we definitely want to store it internally as a list, and we don't want to worry about somebody else changing this. Well, we just want to have a list so we can do what we want with it. We have a draw-on method. So a game object can draw itself on a screen. A screen, again, is just another kind of surface. And so we just call draw centered. So we call draw centered. The first argument is the image that this game object has. So it's a picture of an ant or something. Second argument is the screen that we want to draw onto. And then the third argument is the position. So these things will be drawn so that their center is on a specific position. And then we have a size method that returns the size of this thing, which is just the maximum height or width of the image. Okay. And an ant is just a game object and doesn't do anything else right now except initialize itself. So to initialize an ant, you specify its position, and that initializes its GameObject superclass, where we have to specify the position and the image. So we specify the position to be the same one that we're given, and the image is the image that we get by loading this image from a file. Okay. And now if we look at the game itself, so what we've done here is we've created an ant, and we've set it to have position the width of the screen divided by 2, the height of the screen divided by 2. That's why it shows up right there in the middle of the screen. And if we look at the draw method, here it is. We filled the screen with the background color. I've chosen a pleasant looking almond color, and then we draw the ant on the screen. So the ant knows how to draw itself on a screen. That's one of the ant's methods, so we do that. Okay. So that's what ants are. And similarly, we have an object called food, or a class called food, which initializes itself almost exactly the same way. You specify the position, and it chooses a random image for the image, because we'll have different kinds of food. And its class actually has an initialize method, so before I can create any one of these food objects, I want to have these images already loaded up. So the class itself has an initialize method that loads these images, and so they're ready when it's time to create an instance of this thing. So if we look at how that's used, works like this. We have to initialize the food class. Then we're going to make a set of food items called self.food, and we'll add 4 items to that set, and we'll do that by calling self.newFood. So that's going to create some new piece of food. Let's look at this new food thing. We generate a random position for the food, and it's somewhere randomly picked inside of our screen, but not too close to the border, because we don't want food that's sort of only half visible. So it has to be at least 50 pixels from the left side, and at least 50 pixels from the right side, and 50 pixels from the top, and 50 pixels from the bottom. And we also don't want this food to just show up right on top of the ant. So if the distance between the ant and the food is less than 200, then we pick another location for that food. Okay. So that's what new food does. It generates a new piece of food randomly in somewhere in the screen, not too close to the ant. And finally, we'll fix our draw method. So we have this set of food called self.food, and to draw it, we iterate through it, and we tell each food item, because it's a game object, it can draw itself on the screen. So let's try that. Draw the food, of course. Okay, so there's the ant and the 4 random food objects, and they really are random. There we got super unlucky with the locations, or lucky depending on whose point of view you're looking at. And there's another one. So do you know what these green things are? Kiwis. Do you know what this is? No. Cashew. So it's a cashew. I was surprised by this. I only learned recently on my most recent trip to Brazil that cashews are fruits. The nut thing is this little thing sticking out the bottom. So you dry those and you get cashew nuts that we eat. But the fruit is actually delicious, makes a good juice. Okay. So what we would like is for the ant to chase after this food. Okay, so far it doesn't do anything yet. What we want is the ant to chase after the food. So I guess the first thing that the ant should be able to do is to be able to choose which food they want to chase after. So here, for example, what should the ant go for first? Yeah, the nearest fruit seems like a reasonable choice. It may not be optimal in some sense, but you know, ants are not that smart, so it seems natural to think they might make the greedy choice. And so they'll try and find the nearest piece of food. So that's a choice that's really made by the ant. So the best place to put that is probably inside the ant object. So the code for that should probably go in here. So we can define a method called chooseFoodSelf, and that method will take some collection of food, a set or a list of food items, and it'll pick the best one. So we'll say choose a food item from the all right. So food is you know, a bunch of objects, all of which are in the class food. Self is an ant, and now we want to pick the closest item from food. So how do we do that? So we'd like to compute the distance to each item. So somehow we'll be doing something like calling distance, and distance is supposed to take coordinates. We have coordinates, they're called position. So self.position to something, f. It won't be to food because food is going to be actually a set or a list of food things, so we don't want the distance to the set. We want the distance to some item in that set. And so, for example, that means we're looking for the smallest one, so we'll want to do something like, for f in food, we'll want to compute this distance. Okay, so that goes through and computes the distance for each item from the ant's current position to the position of that food. Now, how do we get the minimum distance, or the closest item? Pretty standard task. Yeah? Well, I want to really, at the end of this, I want to have in my hand the food which is closest. So getting the min will just give me a number, and then that still won't give me this thing. So fairly common task is finding the minimum thing in an array, or the minimum in a list, or the closest thing, or whatever. So we should know how to solve that. Yep. The filter lambda. Filter won't quite do it, because to use filter, we have to specify a function that returns true or false about whether or not we should keep this thing. And we don't really know that until we've seen other things. So this is a fairly common thing. So here's a typical way to do it. You start by saying, what I'm looking for is the minimum distance. So I'll start by saying, well, pick some minimum distance which is huge. I don't know, so 10 to the 15. Think of this as infinity. And now I go through each food item, and I say, what's the distance to that food item? If that distance is less than the minimum distance that I've seen so far, then I do two things. I choose that food item, and I set the minimum distance equal to the distance to that item. Okay. So initially, the minimum distance is infinity. So the first thing I see is going to have some distance that's smaller than that. So I'll choose that right away, right? So the first d that I see will be smaller than d min because d min starts out enormous. So I'll choose that, and then I'll reset d min to be that new distance. Now, if in the next iteration of this loop something better comes along, I'll choose that better thing until eventually, by the time this loop finishes, I'll have chosen the nearest one of those things. Okay. And I'm saving my choice here in a variable called self.choice. Okay. Is that clear? So this is a really standard idiom, a really standard recipe. If there was a number called infinity, we would use it here, but there isn't, so we'll use something that's definitely bigger than the distance that we have to worry about. Our screen is only 800 by 600, so the biggest distance is only going to be something like, I don't know, less than 1,000 probably. So there's no danger there of having no food that's closer than this. All right, so we chose our food. Now what? So the ant wakes up, it chooses its food. So we better do that here. So we create our ant. We create this set of food. So then we'll say ant, choose your food from this set. So the ant has chosen its food now. Yep. Where? I don't see what you mean. Well, we can just run it and see. So it didn't crash. Presumably it made a choice. We'll find out. Okay, so it chose its food. Now, what's the next thing we should implement? So the ant moving to the food. So we want the ant to be able to move. And if we think about the way these games work, right, it's basically an animation. So 30 times a second, the screen is getting updated. So when we say move to the food, we don't really mean just go straight there. Probably this move method is this thing that we want to call 30 times a second, and what we want is for the ant to move a little bit closer to the food at each step. Okay? So a little bit closer to its food choice. And so we need to figure out how to do that. And again, this is a little bit of linear algebra, and so we should maybe draw this a little bit carefully. So we'll have an ant, we'll have a food, we'll have a poison. That's what our class hierarchy looks like. An ant has an extra thing right now called choose food. And now we want to implement move. So what have we got? We have, over here we have our ant. It has coordinates which are called position at 0 and 1. And then there's maybe this ant's choice, which also has a position. Okay. And we want to figure out how to make the ant move closer to this choice. Okay? So what we do is we draw an arrow like this. Okay? So these arrows have names. They're called vectors. And what is this arrow? You can really think of it, it's sort of like a point. It has a part which is an x value, and it has a part which is a y value. Okay. So this arrow here, you really represent it by this x value and this y value. And the way you get those values is you take this position's y value and you subtract this position's y value. That gives you this thing here. And this position's x value and the other position's x value, and you subtract those and you get this thing here. And you have to make sure you do this in the right way. You subtract the correct one, otherwise you'll get an arrow pointing in the wrong direction. So the ant will walk directly away from this food. So first thing we want to do is maybe avoid formulas that are hard to read. So let's say A is equal to the ant's position, and B is equal to the food's position. Remember, self.choice, if you're an ant, is the choice of food that you've made. And now V is going to be this vector, which will be B at 0 minus A at 0, and B at 1 minus A at 1. So it's this thing with two parts. Okay. This is the vector from A to B. So for example, if I were to add V and A together in the natural way, where I add the x coordinates together and I add their y coordinates together, well, then I would just get the location of the food again. Okay. So V plus A, so the way to think of that is V plus A is equal to the location of the food. Okay. So back to this picture. So now we have a vector that leads to this food. That's fine. This vector tells us how to get there, but there's something sort of a little bit wrong, or that we can't quite use this vector yet, and that's because it's too long somehow. It will take us straight to the food choice, and what we don't really want this whole vector. All we really want to know is what direction it's pointing in. So I want to do what's called normalizing this vector. So I want to make it so that it has a length which is fixed. So I want to make its length equal to 1. So right now, what is the length of this vector in this picture? Yep. Yeah, I mean this vector points from A to B, so the length is the distance between A over here, which is the ant, and B over here, which is the food. So it's just the distance. Well, and if you look at the distance is just x squared plus y squared, and then the square root of that, right? So let's figure out the length of this vector. So that's just x squared, which is v0, plus y squared, which is v1. And we want to take the square root of that. Equivalently, we could have just called our distance function that we've already written and said n is equal to the distance from A to B. Same thing. This would do exactly the same thing, because the distance function just takes the difference in x coordinates and the difference in y coordinates, squares them, adds them together, and returns the square root. The reason we don't do that is maybe this is a little more efficient, because now, since we've already computed these differences anyway, we might as well just use them rather than have the distance function compute them again. Okay? And we call this thing n because in linear algebra, this thing is called a norm. So it's the norm of that vector. Okay? So back to this picture, we have this n is really this length of this thing here. So if you imagine this is a length, then that's n. Now, we want to make our vector be short. We want it to have length exactly 1. So how do we do that? So right now the vector could have any length. I mean, it just depends on the distance from A to B. So how could we make it have length exactly 1? Yeah. So to make the vector have length exactly 1, we say, so we'll call this thing UV, stands for unit vector. We just take V's coordinates and divide them by the norm. Right? If V has length n now, if we just make it smaller by a factor of n, then it has length 1. Okay? So this UV is the unit vector that points from A towards B. Okay? So it's a vector of length 1 that points from A and moves towards B. All right. Okay. So now we're ready to make the ant move, because what we have now is a vector that looks like this. It's 1, its length is exactly 1, and it points from A towards B. So, so how do we make this thing move then? Yeah, so we add this vector, which is of length 1, pointing from A towards B. We add that to A. And if we do that, then A is going to move to here. Right? So this vector will take A from this location and move it to this location, which is, you know, a little bit closer to B. So we'll say, so A is the position of this thing. So we can say A at 0 plus equals UV at 0, and A at 1 plus equals UV at 1. And maybe to make it a little bit more clear, A refers to self-position. So just to make it clear for the reader of the code, what we're really changing here, whether I write A or self.position, they both refer to the same thing, but maybe it's a little bit easier. To do this. We'll say, take a step towards B. Okay. All right. So that's how an ant moves. So the recipe is, if I want to get from A to B, I figure out the vector that takes me from A to B, I make it a specific length, in this case its length is 1, and then I move that distance. So take the vector from A to B, normalize it, and then take a step that way. Now when do we want to do this? Well, we want to do this 30 times a second, and so So when does that happen? Well, after we draw, so we draw 30 times a second, maybe we'll do our move, and so we say self.ant.move. Let's try that. So there we go. The ant made its choice, and now it's moving towards this thing. Now, and then it gets there, and it's stuck. It's just walking back and forth over this thing. Okay, so success there. Now, lots of things to go wrong. For example, common pitfall is to do something like take the vector in the wrong direction. So now the ant just runs away from the food. Or another common one is to screw that up. And now the ant is actually trying to get to that food, but it's running sideways from it. Okay, so these vector calculations are kind of important. You have to do them right, otherwise you get situations like that. Okay. Luckily, in things like games, these things are fairly obvious when you've made a mistake. You see the problem right away. Okay, so here's one issue that is a little bothersome now, is it's a little bit slow. I mean, it's certainly an issue that the ant gets there and nothing happens, but that's because we haven't done that yet. But the ant's moving a little bit slowly. So how would we change that? Yeah. So if we want this thing to go faster, we should right now the ant is taking one step in that direction. And if we want it to go faster, we should take it, rather than travel a distance of 1, we should have it travel a distance greater than 1. So we'll have it travel some number called self.speed, which we can tweak, and maybe as the game goes on, we can even change. So an ant will then have a speed, and let's make its speed something like 7. So now it should get there 7 times faster. Yeah. There we go. So here's a question for you. When it gets there, it starts this vibrating back and forth. So why is it doing that? Yep. Because it's always, right, so what we did was we took this vector, we made it into a vector of length 1, and then we multiplied it by 7, so now it's a vector of length 7. So at some point, the ant gets close to the food, within a distance less than 7, and then it travels a distance of 7 towards the food. So it actually overshoots it, and now it's on the other side of the food, so when next time it computes its vector, it's pointing in the other direction, and it takes 7 steps in that direction, which overshoots the food again, so it's just jumping back and forth over this piece of food. So if you wanted it to really land on the food, you'd have to add a little bit of extra code here to say, if the distance between the vector, the ant and the food is less than the speed, then you don't multiply by the speed, but you just multiply by that distance. We won't worry about that because once the ant gets close enough, it'll just, the food will disappear. It'll eat it anyway. Okay. So that's good. We have the ant moving closer to the food as it's supposed to. Now we would like the ant, when it gets there, for the food to be eaten to disappear. So where would the code for that go? Where's the natural place to put that? What's that? We could sort of put it in the food, but food doesn't really know about ants. ants know about food, so it would make more sense in the ant. But if you look at the things we'll have to do, basically the ant gets to the food, and then we want to make the food go away, and who's keeping track of the food, of all the different foods? Well, it's actually the game that's keeping track of that. So if you think of the task we're trying to do, we want the food to disappear from the game. It's actually the game that's keeping track of all that. So it makes sense for the game to detect when the ant has reached the food. And when should it do that? Where's the natural place to do that? Well, at what point? So the game is constantly redrawing this animation 30 times a second. It draws a picture, the ant moves. It draws a picture, the ant moves. Draws a picture, the ant moves. Yeah. Yeah. So right after the ant moves is maybe when we should check to see if it ate the food. Okay. And so it wants to eat the food if the ant is very close to, or the ant should eat the food if it's very close to its choice of food. So that means we want to do something like measure the distance from self dot ant, the position of the ant, and the ant's choice of food, its position. Okay. So if that distance is small, and now what does it mean to be small? So what does it mean for the ant to be close to the food? Less than the ant's speed pixels away, so we can try that. All right, so once it's that close, what are the things that should happen? So the food should disappear. So we want to remove from food, which is a set, we want to remove the food that the ant has just gotten to. Okay, so we remove that food. What else? So we want to make another piece of food? Or re-choose the food? Let's choose, okay. So self.ant.choose food. Let's say self.food. So it'll have to make a new choice. Perfect. Then there's a crash because there was no food left, and the ant somewhere in the choosing the food there was some issue there. So we maybe want more food to appear. We don't want this thing just to run out of food. So maybe we'll do so when the ant eats a piece of food, a new piece will appear. So it eats the food, goes to the next closest piece, eats that, eats that, eats that and that, that and that, and so on. Okay. So it's a pretty efficient ant. Okay. So is that clear, how all that works now? So these things can get a little bit difficult to follow because somehow the logic is spread out across different locations, but I think we have a good idea of what's happening now. All right, so I want to add to this game some poison. So that means I want to make a class called poison. So does anybody have questions about any of that stuff right now? It's clear. So have you guys used vectors before? Have you talked about vectors in any math class before? Yeah, no. And where did you learn these things? Okay, so if you took some, it's not clear anymore to me which courses you guys have to take to get into this program. So some of you may or may not have taken courses that talked about vectors, but they're really useful, and you've got to use them. And poison is a lot like these other things. When we create it, we'll say where it is on the screen. It initializes its parent. With its position and its image. I think its image is poison.png. Let's look in the images directory. Poison game. So one thing you may find yourself having to do a lot is learning some kind of basic image editor, because usually the images that you download from Google Advanced Image Search, they're typically really big, much bigger than you need for a game, so you want something that's able to scale images. So use whatever your favorite image editor is. If you're having difficulty finding one or choosing one, post a message on the forum, then everybody will, you'll get some recommendation from someone and everybody will get to see it. Okay, so that's our poison class, and we should maybe make this poison show up at some point. So for example, when the game starts, maybe there should be some poison. And that'll be something like similar to what we did with the food. I don't know, how much poison should we put out? Lots of it? 8? And again, we probably want to, so we want to write a method for creating new poison, and we'd like this game to be a little bit fair, so we don't want to put poison right on top of the ant immediately. So we'll actually borrow this code. We probably could have, if we had been a little bit more careful, could have reused the code. Okay. So this will pick random positions for poison, and discard them if they're too close to the ant. And so you won't start out with any poison right on top of the ant. All right, so that generates this new poison. Let's test everything. Didn't crash, so our code is working, but what's missing? It's there in the game. It was all created, but where's it missing from? Why are we not seeing it? Because we never drew it. So in our draw method, we draw the ant, we draw the food for P and self.poison. P.draw on self.screen. Okay, so now we're starting to see, it's difficult to see sometimes early on what the advantages of objects are, but now we're starting to see that, right? We just created a new class that just has one method, the init method, and yet that instances of that class know how to draw themselves and other things because they inherited that from their parent object. All right. So let's see if that works. There we go. Lots of poison everywhere. Do you see maybe any other unfairness issues in this game? Well, you can't do anything, and, well, the ant just walks right through the poison, so it's not complete. But maybe about our choice of poison locations. Any issues that might crop up?
You have to be far apart from each other, I guess?
Yeah, could be far apart from each other. Bigger problem is if you put him on top of the food, then the ant's kind of screwed. He's going to be forced to walk into the poison. But maybe we'll leave that there and we'll let the user deal with that. Or maybe you want to spread them out more nicely. So this new poison and new food method maybe could use some other fine-tuning, but good enough for now. Okay. So one problem right now is that the ant can, well, actually there's a couple of things. So one is the drawing is a little bit strange. So if an ant walked over to a piece of food, would it normally crawl underneath the food? Or would it crawl on top of the food? I mean, an ant's teeth are on it, on the bottom of its mouth, so it would sort of crawl on top of the food to eat it, right? And here, it's going underneath the food and it's disappearing. So maybe we should fix that little rendering bug. How do we fix that?
Draw the ant for the food.
Yeah, we draw the food first and then we draw the ant. And maybe the same issue, we'll fix the poison issue while we're at it. We'll fix the poison issue so the ant walks over the poison instead of underneath it. Cool. There, that looks better. All right. Now, poison should kill the ant. How do we do that? Where and how? In the ant's method? So, does the ant know about the poison? No. So, the only thing that knows about both the poison, all of the poison, and the ant is the game. So, it's probably the game that should detect if the ant is eating the poison or not. And it might as well do that, right? The game already detects if the ant eats the food. Maybe it should also detect if the ant eats the poison. Okay. So let's not let this get too long. So we can do self.foodCheck. We'll just copy all of that out of there. And while we're developing, we'll just put it in here. So now we'd like to know if the ant is being poisoned. So when is the ant being poisoned? Well, when it's on top of some poison. How do we check if the ant is on top of some poison? Yeah, so we want to compare the position of the ant and the position of the poison. And there's a lot of poison, so it's not just one poison that we're worried about, it's all of the poisons on the screen. So it's going to be some kind of loop. So for p in self dot poison, and we're going to have some check this, the similar if the distance between the ant's position and p's position, if that's less than something, then we should do something. So let's just write something. Then what should happen is the ant dies, right? Yeah? Okay, so then we'll do something like, say, so we'll just stop playing the game, let's say. You only get one shot at it. We can change that. And whatever happens. Okay, and what about this distance here? How small should this distance be? So we can do the same thing we did for the we can do the same thing we did before for the food and say self.ant.speed. So right now that's 7 pixels. We can try that. Not quite enough, eh? So that's not big enough. We can we can try something like, I don't know, 100. Well, actually, let's just make sure this thing dies. So he's not really hitting that section of code. And it's getting awfully close to the poison. So we can try something a bit bigger, maybe 100. Dead. So that was a little bit too big. And so maybe the best strategy then is to base this on, well, we already know that game objects, where are we? Game objects can tell you their size. So really, how close is too close depends somehow on the size. So let's say if the distance is less than self.ant.size plus p.size, maybe divided by 2. There we go. So that was a pretty good time for the ant to die. Yeah, pretty much as soon as it touches the food. Okay, so so that takes you into the game over state. And so let's play with this a little bit. So I've introduced this thing called state in a game. I better give it different values. Game over equals 1. playing equals 0. So initially, the state of the game is that it's playing. Eventually, the state of the game could be game over. And now we need to add some logic to do different things depending on the state. So if the state is that we're playing, well, then we play, and we do all this stuff. If the state is game over, we don't do anything. So let's see if that ends it a little more cleanly. There. So now the ant's been poisoned. The state is game over, and that's the end of the game for the ant. So everything just stops. We don't do any more updates. What does a typical video game do at this point? Yep.
Prints out game over in big sad letters.
It prints out game over in big sad letters. Okay? So let's make some big sad letters just so we can print game over. And what's a good color for us to use? Black? Black. So black is 0, 0, 0. Okay, so that makes that'll make a piece of text for us. So in order to make text in this thing, you have to create a font. This says, give me the system font. And it should be of size 100. And then in that font, render the text game over, use anti-aliasing, and use the text color black. All right, so that makes this thing. Save a game over surface. And in our draw loop, state is game over, then we should draw that. Let's see if that works. There we go. Draw centered takes exactly 3 arguments, of course, because we have to say where we're drawing it. So we take the game over text that we created when we initialize this thing, We want to draw it on the screen, and we want to draw it in the center. Game over. Okay, good. And, well, so that's, I think that covers just about all of the things almost all the things you'll need to know for this assignment. With that and last class, you should be good to go.